Hi, everyone, and welcome to Inside the Lab. It's our new spin on taking webinars to the next level. In this type of webinar in this series, you're going to be able to interact with some of our favorite experts in the field of various either applications, techniques, or types of chromatography. So we hope that this is a little bit more of an engaging type of webinar where you're able to ask questions about any topic. We're going to kick it off and start it. So my name's Simon Lomas. I've been with Phenomenex for about 15 years. I'm currently the manager of the product marketing team and was woken up by my son with a pterodactyl scream and a finger in my ear this morning. So times are changing, a little bit different. Now I'll introduce you to our experts. So each one of them will give you a quick background, and then I'll talk more about how this is going to work. So we have Dr. Phil on the line, Dr. Phil Kerner, Dr. Jason Ansbach, and Zishan Akil.
Hi, everyone. My name is Dr. Phil Kerner. I've been with Phenomenex for 21 years. Prior to that, I spent 11 years in the industry, so doing a lot of HPLC, but also some GC and sample prep, SPE, in my previous life. Yeah, I go by the moniker Dr. Phil. I guess that somebody decided that was kind of clever a few years ago. And so just in this format, I'm happy to entertain separation science, chromatography questions, but if you get into personal relationship questions, I'm gonna have to defer to Zishan.
Oh, there you go. Hi, everyone. I'm Sean Akil. I'm celebrating my 10th year at Phenomenex. Very happy to have that. I've done a little bit of everything at Phenomenex, from LC to GC to SPE. I primarily work in a group called Phenologics. It's our applications lab group. So a lot of our published apps that you see on our website or you get in your brochures, a majority of them do come through our group. So if you have any questions that you've seen on apps in the catalog or so on, feel free to throw those over our way. So here's Jason.
So I'm Dr. Jason Ansbach, aka Dr. Spock. I'm celebrating my 15th year at Phenomenex and my 20th year in the industry. For 14 and a half of those 15 years, I was in the R&D group here at Phenomenex, specializing in column packing and hardware. I've recently taken on the role of global product manager of HPLC. My specialty is theoretical chromatography, specifically high speed, high efficiency separations. So any questions you have, how to optimize separations, speed separations up, scaling, instrument modifications and things like that, I'm your guy.
Cool, thank you all for your background. And just to add one little tidbit, because Zishan is currently in a car, we're thinking maybe in the future we might do a chromatography cash cab or carpool karaoke, but we have to wait till the pandemic kind of settles down a little bit. So thank you, Zishan, for adding a little levity to this situation.
Yeah.
Okay, so we're going to kick this off. As you have questions about any topic, so the 4 categories we're going to hit upon in 15-minute segments are core shell and fully porous particle morphologies, mobile phase systems, selectivity, and sample prep related to HPLC Basics. So as we get to each one of those categories or throughout the webinar, please in your chat box throw the questions in, and then they'll come my way, and I'll have one of our experts give their answer to it. Cool. Looks like we have one coming through already. So I'll give this one to Dr. Phil. Is there a difference in loadability when comparing a column packed with superficially porous particles and fully porous particles?
There is. The primary reason loadability is related to surface area and to some degree carbon load, but specifically surface area. So fully porous materials typically, as their name implies, just are much more porous than a core shell silica particle. Core shell silica typically entails a solid non-porous core at the center, or the core, obviously, of the particle, and so as a result doesn't contribute much in the way of surface area. So it's just that porous shell surrounding the solid core that really contributes to surface area, and then also the amount of bonded phase that's attached. So yes, typically fully porous materials will be a bit more retentive because of the higher carbon load and the higher amount of stationary phase that's attached, but also give you higher loadabilities just in terms of mass loadings.
Thank you. Okay, we got another one coming through. I'll send this one to Zishan. I work with LC-MS type analysis. Would you recommend starting my initial selectivity screen with either a core shell or fully porous column, or a combo of both?
Well, you know, a lot of my preliminary screens are usually done on a fully porous, just to see, you know, sometimes you have something that's very polar, doesn't retain very well. It's always nice to have a fully porous phase so they can retain as much as you can. Sometimes things just fly out in the void. Core shell is great for LC-MS final method because you get a great, nice sharp peak. But you know, for me, I typically lean more towards a fully porous just to start off with, and then optimize later on with a core shell particle.
Gotcha. Thank you. All right, Dr. Ansbach, this one's for you. In comparing core shell and fully porous of a similar column dimension, phase on the same system, would you see a sensitivity difference?
You definitely would. If you're comparing two particles that are about the same diameter, a core shell particle will give you anywhere between 25 and 50% more efficiency, meaning narrower peaks. And anytime you give narrower peaks, you're always going to get a higher peak height or more sensitivity, better signal to noise.
Perfect. Thank you. All right. Looks like we got one more coming through right now. Dr. Phil, in regards to detectors, is there an advantage to using a certain type of particle morphology with certain detections strategies? For example, like LCUV versus tandem aspect?
Well, to follow on to what Jason mentions, when you use core shell materials, you're going to get narrower peaks, higher efficiencies. So if you have slower data acquisition rates, slower scan rates, say for a mass spec, or just a slower acquisition rate in terms of how many data points you're collecting across the peak, then you're not going to realize that full benefit. So you really need to have a faster acquisition rate, and that's easy. On the LCUV side, you can change your data acquisition parameters. So you can go a little bit faster, collect more data points across the peak. And typically, the rule of thumb is somewhere between 15 to 20 data points across the peak to accurately measure it. If you don't have enough, then the smoothing function starts to make some approximations, and you'll see that the peak doesn't look nearly as good as you think it would. One of the challenges with mass spec is if you're doing full scan and you've got those really narrow peaks, you may not acquire as many data points across that. So that's where selected ion monitoring, or monitoring specific mass transitions, so that you're dwelling on that ion or that M over Z a little bit longer, so you're able to acquire a little bit more data. So that's one of the considerations. If you've got a system where you can't adjust the acquisition rate very well, or you can't go a whole lot faster than, say, maybe 5 hertz or 5 data points across the peak, or per second, I'm sorry, then if you've got peaks that are 1 and 2 and 3 seconds wide, you may not acquire enough data. So you might be better off then using a lower efficiency material. So.
Thank you. Dr. Ansbach, I think I'm going to throw you this one. I heard core shell and core shell or superficially porous products offer reduced back pressure compared to similar column pack with fully porous. Have you seen this from a manufacturer side?
You know, it's a tricky question because as one of the panelists, I think it was Phil, was explaining that, you know, you have a volume of the column that's taken up by a non-porous core. So the overall porosity of the column is lower on a core shell column than it is on a fully porous. So at the same flow rate, you will actually get a higher linear velocity on the core shell column than you would on a fully porous particle. So it doesn't really affect the pressure, but it will affect your T0s. The amount of resistance to flow will be about the same, but it's not uncommon to see, you know, a 15% reduction in T0 at the exact same flow rate on a core shell column versus a fully porous column. So yeah, again, it's not really a back pressure thing, but you could see you know, reductions in T0, and sometimes you need to take that account if you're going to scale from a fully porous to a core shell.
Gotcha. So you know, like a 5 micron core shell and a 5 micron fully porous are pretty much going to give the exact same back pressure.
Within the variability of column to column, I mean, it's not going to be significant.
Gotcha. Thank you. Zishan, have you seen a lifetime difference between columns packed with you know, core shell or fully porous products?
So on a practical standpoint, I mean, you have less surface area, you know, because you have a solid core on the center. So it depends on your sample matrix. I mean, if you have something that's very dirty, it's prone to clogging a core shell column relative to a fully porous. So the analogy that I use for customers all the time, like fully porous is like a kitchen sponge, like, you know, it's very porous, but on the outside it looks fine, but on the inside there's all this gunk and goo in there from God knows what that you've injected onto there. So, you know, core shell, it's a wonderful phase, high efficiency, but, you know, you need to treat it right with our security guard cartridges that are a guard column that basically protect it from anything that might gum it up every so often. So with the proper precautions, you know, you can have you know, pretty nice lifetimes on the kinetics on our core shell particles.
Gotcha.
If to add to that, one strategy you can also employ is, because you do get so much more efficiency on the core shell particle, a lot of times you can actually use a bigger particle and get the same efficiencies that you could on a smaller fully porous particle. So you can actually go up in particle size, and by doing that you get more space between the particles, more resistance to plugging. So that's another strategy that you can use to get higher lifetimes out of core shell.
And lower pressure, yeah.
And that's traditionally what we've seen, right, guys? So the 2.6 micron core shell particle being used, you know, in place of a sub 2 micron, and then basically you're able to, you know, achieve some incredible performance on that level with, you know, being able to speed up productivity, which ultimately can potentially save you, you know, quite a bit of money in terms of solvent.
Yeah, so when you've got the smaller the particle size, typically the narrower the particle size distribution for fully porous materials. And so sub 2 micron, you know, they're going to pack really tightly into the column, and core shell materials are even more monodisperse. And so when you take that same particle size and pack it, it's going to be packed even tighter, so you don't have as much space around the particle. And so again, if you're a little bit lazy or sloppy, or just, you know, some people don't like to do much in the way of sample prep, and so dirtier samples may clog a core shell material faster, and so you're not sacrificing much in the way of efficiency by going from a sub 2 to say a 2.6, 2.7 core shell material, but it's gonna be a little bit more forgiving than a sub 2 micron fully porous in that regard.
Yeah.
Cool. We're gonna Dr. Ansbach for this one. Is Phenomenex planning on expanding, you know, both core shell and fully porous product offerings, or focusing on one or the other for future phase development?
We're not really going to be focusing on one or the other. We feel that both particles are important to have in your toolkit, and there are definite times when you want a core shell, and there are definite times when you want a fully porous. So by having a full product line selection of both types of particles is important. I would say that, you know, in our Luna Omega line, that there are plans to expand that line maybe a little bit faster than some of the core shells at this point, but we don't believe that we believe that you should have a full product offering and a full toolkit of selectivities in both style particles.
Yes, thank you. It looks like we got one that says, what type and size of filters, I'm assuming this is syringe filters, are recommended for samples that are run on core shell columns? Throw this your way, Z.
I commonly use 0.45 micron. We have both nylon and PTFE/Teflon in our lab. You know, if your sample is more organic in nature, we tend to go towards the PTFE filter, and if it's more aqueous in nature, we tend to use the nylon filter more often. And those are pretty good because without giving away too many, trade secrets, I mean, it's a pretty good way of making sure that the sample is pre-filtered, so it doesn't clog up anything that's on the pre-filter on the column.
Yeah, I just add that I know that John Dolan, who's now retired, but in his series of LC/GC troubleshooting columns, going back many years, but when UHPLC started to become much more popular, widely used, more widely used, he authored a column in LC/GC, something around the concept of what he called chromatographic hygiene, and he recommended filtering with 0.2 micron if you're using UHPLC columns. And the one caveat here, of course, is you have to remember that a filter for filtering your samples is only going to remove microparticulates. It's not going to remove other excipients that are soluble or in the sample diluent. So, and if any of those components get into the mobile phase and they're not soluble there, that's still going to create a problem. So that filtering your sample is really just to remove microparticulates. And if you're concerned about certain matrices, it might make sense to use a smaller particle size, but then maybe to follow on what Zeishan mentioned a little bit earlier too, that's where guard columns can be really effective, because not only will they filter out particulates, but they will also remove any strongly retained components that might otherwise clog the analytical column.
You'll save your thumb because those 0.2s are really hard to push on a syringe filter.
It's a good workout in these days, man.
Yeah.
All right, it looks like this is a good segue into mobile phase systems. So I have a question for Dr. Phil. I understand acetonitrile can break down to exposure with light. What effects should I see on my LC screens if my acetonitrile breaks down in the reservoir?
Well, you'll see if any component in the mobile phase breaks down, you may see, but specifically in organic, you might see extra peaks or ghost peaks, small little peaks that start to show up, and mystery peaks that we otherwise have not been seeing. And so that goes back to just basic troubleshooting. Remake the mobile phase, just replace it, use a fresh reservoir, and if the peaks go away, then it's an indication that you've stumbled on the right contributor. Yeah, a lot of times you'll see it's not just acetonitrile, but other components in the mobile phase that might degrade over time. TFA is one classic example. One reason why it ships in a brown bottle or in brown snap ampules. People that use the larger bottles sometimes will see over time, they'll start to see spurious peaks showing up due to mobile phase, which just break down. That's one reason why I always like to use and always recommend the 1 mil snap caps of TFA, because then you use it and then you need to make up more mobile phase, you use a fresh ampule, and you can avoid having that type of mystery peak carryover, ghost peak type situation.
Well, and you also have to be careful when you're doing volatile additives like formic acid. A lot of people don't realize that on most mobile phase bottles, it's actually open to the atmosphere, because as liquid goes out, air's got to get in. And so if you have just a standard mobile phase bottle cap, the things like formic acid can evaporate over time. That's why things like the security cap that has a one-way valve on there so that air can come in but it can't go back out can also help prolong mobile phases.
I'd like to add just to Dr. Phil's point also, perchloric acid is another one that's very common to just tends to go brown on you when you use it once or twice. It can go bad pretty quickly. And just recently, Dr. Phil and I were talking about the DMSO and how if you run a blank, at least you know what that like the diluent blank. So then you know that that's the suspect peak relative to you have no idea what it is. So it's always run those blanks, those diluent blanks, those solvent blanks, so you can always figure out what that evil extra peak is.
Those evil peaks. Mm.
I know, phantom.
Okay, that's a good segue into, are there any industry standards for setting mobile phase expiration dates? Leave this open to anybody who wants to answer.
In our
I don't know
lab,
if
we do 6
ahead,
months.
Dave.
Sorry, Dr. Phil. 6 months for 100% pure solvents and 3 months for salt-made buffers and so on. Go ahead, Dr.
Well, it's really kind of tricky. We have a pretty, I would say, rigid series of recommendations in the R&D labs. As Aishan says, if it's 100% organic, then a lot of times we'll say it's 6 months. If it's very acidic, we'll say a month. If it's at neutral pH, we usually recommend that you use it only for a week. Neutral pH tends to promote bacterial growth. But again, if you use things like security cap and other ways to isolate the mobile phase from the atmosphere, that can give you more longevity of your mobile phase. But it's also a good idea once in a while to flush out your lines with things like isopropanol and stuff to make sure that if you did have any bacteria growth that you flush it out of your system.
Yeah, Zishan and I've seen, unfortunately, this arise, especially in pharmaceutical QC labs where they might make up things like phosphate, buffer, pH 4.5 because that's what the method calls for, and then they try to use that over an extended period of time.
Peaks.
Not only can you, so you have a couple potential issues. To go back to one thing Jason pointed out, you can have bacterial growth. Phosphate, unfortunately, is pretty good growth medium for that, even at a less than neutral pH, like moderately acidic. But the second thing is that because it's not really buffering at that pH, the carbonic acid from the CO2 that we all exhale in the laboratory is absorbed in that aqueous buffer and produces carbonic acid, which then can tweak the pH. And if it starts to creep down from 4.5 to 4.4, it doesn't have to be that much of a change. It depends on how sensitive your method is. You can start to see peaks moving around. And so that's one reason why I always like to see people make up mobile phase fresh, especially when it's, Jason mentioned 0.1% formic acid, because the formic acid is volatile depending on how you're storing your mobile phase in the reservoir when you're in between days, and the same thing with things like phosphate as well. So anything that's volatile you want to be careful of, and anything that's really not in the buffer range for that specific buffer salt, you want to be careful about. Probably make it fresh more often than not.
Thank you. Dr. Ansbach, I'm going to send this one your way. Do you have a recommendation for a step-by-step approach to testing out mobile phases for relatively basic molecules?
Basic molecules, you a lot of times you have two real choices. Either you run at low pH and make sure they're all deprotonated, so they're all in the same charge state, or you run at high pH and hope that you can get the pH high enough that you make them all in the neutral charge state. What you really want to avoid with any acidic or basic component is being anywhere within about 2 pH units of their pKa, because then you're going to have a charge distribution, which is going to, at the very least, give you wide peaks, but in certain cases, it'll actually give you split peaks. So my recommendation for basic compounds is whenever you can get the pH above the pKa, significantly above the pKa to make them neutral, that's where you should live. There are, I would say, restrictions to that. There's very few columns on the market that can handle high pH, and most of them are limited in the 10 to 11 pH range, even the quote-unquote high pH columns in reverse phase. So if you can't get the pKa or the pH above the pKa, then the best is to run as low of a pH as you can get away with, just to make sure they're all charged.
Thank you.
For basic compounds, I was just going to add, just for basic compounds at low pH, they'll be charged, but as Jesse mentioned, they'll be in the same charge state, but you also minimize any potential silanol interactions with silica-based materials as well. And then if it's not, maybe getting ahead of ourselves, but then if you don't get enough retention, you go to high pH like Jason mentioned, or you start looking at for other phases that maybe give more polar retention and polar interactions at that low pH.
Or even a charged phase that may actually offer a significant increase in peak shape and sensitivity, right?
Correct.
Z, do you have any tips on using other organic mobile phases outside of acetonitrile?
So acetonitrile is nice because it's relatively fast with respect to, like, for example, methanol. Methanol is cheaper, but it has its Achilles heel that it's higher in back pressure. The viscosity is a little bit higher, so that there's that. But both offer different selectivities, so it's always good to run both because you never know how your analyte's gonna interact with the column and everything. So it's always, for example, with kinetics biphenyl, we've seen great benefits of using methanol relative to using acetonitrile for certain cases, but you only see those certain cases unless you run both. So we always recommend to see how phenyl phases tend to work with either methanol or acetonitrile. In the lab, we typically, the most that we've ever seen in terms of other than acetonitrile, I mean, we tried the acetonitrile methanol. We use sometimes isopropanol as an additive. We rarely see it as a full-on mobile phase unless you're running chiral HPLC under normal phase or something like that. But for reverse phase, we tend to just stick with methanol, IPA. Sometimes we have an additive of THF here or there, more or less. So that's usually what we use.
I was just going to add, related to the biphenyl, but all phenyl phases, you'll typically see more of that pi-pi selectivity and interaction when you use methanol because it's not, it doesn't block that pi-pi interaction, but it's not to say that you won't see it with acetonitrile. And then customers sometimes hesitate because methanol is, as Zishan mentioned, is more viscous methanol water mixtures, so your pressures will be higher. But we've actually done an interesting study where we looked at mixtures of methanol with acetonitrile, different percentages with some of our different phenyl phases. And there's actually a nice tech note that came out of our phenologics group. If anybody's interested, that just kind of highlights, you can see that it, as Zishan alluded to, it depends on the compounds. Some compounds you'll see the effect of methanol being much more significant than others. In some cases, the acetonitrile is a better option. So it's good to explore both.
Dr. Ansbach, back to the subject of acids. Everybody seems to be using 0.1% acid in mobile phase. Is this the best acid concentration? And does ESIMS require that amount of acid?
It's become industry practice. Obviously with anything, there's always optimization that you can do. Especially when you're in LCMS, though, you do need that acid to help you with your ionization. But if you go to too much acid, then you start having ionization competition, and it starts giving you some adducts, which complicates your deconvolution of your mass spec. So, to say that there is like a rule in chromatography is always a bad idea. What I always say is that 0.1% is a good starting point. If you're loading a lot of mass onto the column, you may want to try going to say 0.2% in certain cases, because you may be stripping the local pH around your analyte band might actually be higher, and that would be a reason why you might want to increase it. But you always want to use as little additive as you can, as to not have other competitions, especially when running at LCMS or even in UV. Some of the additives can raise your background and lower sensitivity. So
Thank you. Z, I'm going to throw this one your way, and Dr. Phil, I'll throw you the second one. These are both about gradients. So Z, do you have a suggestion for a scouting reverse phase gradient for, like, let's say, small molecule analysis?
Yeah, that's one of my most common questions. It's usually for me, I start at about 2% organic, whatever it is, pseudo-nitrile or methanol, and you know, you could have acid in there. It really depends on the analyte. I would look at on chemicalize.com or something and take a look at how the structure looks. But generally for gradient profiles, I put about a 30-second delay right in the beginning. And then I do about, depending on the length of the column, say for example, a 10-centimeter column, I probably do a 10-minute linear gradient up to 95% acetonitrile, assuming that there's no salt in your A line. It's just water and, say, for example, formic acid. And then I go up to 95%, hold it for about a minute or two, and then bring it back down. And then depending on where the peak would show up, or many peaks, you just basically try to scale that gradient into something a little bit more shallow so that you give your analytes more time to separate in that space.
Cool. Dr. Phil, when using a solvent gradient, is there an advantage to using two pure phase elements, like 100% acetonitrile, 100% pure water, versus two combo elutant mixtures, like 70% acetonitrile or 30% acetonitrile?
So you're talking about, maybe A would be 95% water, 5% acetonitrile, and B would be 95% acetonitrile, 5% water. That is a little bit more common. I've run into this in the past, and again, this is maybe it's because I'm an old school guy, and some of the systems probably don't have these issues now. But when acetonitrile and water mix, it's an endothermic interaction, and you actually, if you do this in the lab, the vessel will actually get a little bit cooler, and as a result, you get a little bit of what looks like outgassing. So that can create a little bit of problems depending on your system. And so back when I had this problem and I was using like a Beckman 1 single piston pump, that became a big issue because of the noise from this outgassing that hit the detector on the back end, and that was the only thing we could kind of figure out that was going on. I don't think that's really an issue with the newer, more modern systems where you've got onboard degassing and such, but you'll see people that just that will do water in A and acetonitrile in B and then just start, but very rarely would somebody go from, say, 100% A to 100% B, so 100% water to 100% acetonitrile. It would be more like what Zishan was saying, where you might start with 3 to 5% of your organic and then run your gradient out to a higher percentage of organic. And if you're doing that, you probably can get away with just the pure solids in A and B. Part of it is, and again, it's going to depend on methods and such. You might want to start with 5% acetonitrile in your A with 95% water, especially if you're going to start at 100% A, for example. Then you already have 5% acetonitrile there, so you're not mixing pure solvents right off the get-go. I've never actually seen that that's a problem in the more modern equipment, so I don't think it's not a bad thing necessarily. And so maybe some of the folks attending might have seen something like that as being problematic, but I think on the modern systems, I don't think that's really an issue.
Thank you, Dr. Ansbach. This one comes in the topic of temperature. How often do you use mobile phase temperature to optimize your separation?
I'm assuming you mean column temperature, not mobile phase temperature. Temperature can be a powerful tool to help you tweak separations. I mean, in general, as you increase the temperature, you will sharpen your peaks. You'll lower your viscosity, allowing you to run higher flow rates at the same pressure. But what you usually sacrifice is retention. But the retention changes unless you have 100% hydrophobic interaction, which is not the case most of the time. Is not going to be the same on every peak, depending on what type of interactions. Like what I'm getting at is ionic interactions are less affected by increases in temperature than hydrophobic. So if you have something that has more ionic interaction than its neighbor that has more hydrophobic interaction, you will see changes in elution order. So I would say that temperature generally is not the primary tool that you should be using to optimize separations. But if you get a separation like 75% of the way there, I think it's a commonly overlooked tool that you can use to try and get that last 25% of the compounds resolved that are not cooperating.
Thank you. Okay, let's do a quick segue. So, Dr. Phil, how do you account for differences in system dwell volume when developing a method that will be transferred?
Well, the good news is most of the modern systems, well, and the chromatography software can help you with that, whether it's in Power, ChemStation, et cetera, depending on your chromatography data system of choice and what instrument you're using. So a lot of times you can account for that. And I know Zishan's, we run into this more recently when we're trying to replicate gradient methods, specifically a couple European pharmacopoeia methods that said, you know, we're using this column and on a system that has this dwell, but then we've got, even if we're using the same column, to put it on a different system, you've got to make adjustments for that. So that's a consideration that has to be taken into account. So typically, if you've got a, let's see, I'm going to get this, and Zishan, you're going to have to correct me if I get this backwards, because you've done this more recently hands-on. So if you've got a system dwell volume of, say, an HPLC system that's close to 1 mil, and then you're going to transfer this to a UHPLC system that's got maybe 300 microliters, so 0.3 mil dwell volume. And so the method works on the HPLC system, but you want to transfer it to the UPLC system or UHPLC system. Then you've got to change the isocratic hold time. You've got to kind of you've got to increase it to kind of get you closer to where you're kind of coming in that dwell exactly, and then the gradient from then on. So that's typically the first thing you want to start with, and then vice versa. I guess if you've got a UHPLC system method developed, and then you want to go to an HPLC system with that, obviously with probably changing the particle size, because you're not going to run a sub-2 on an HPLC system, at least not at the same flow rates, and make that reverse adjustment. You probably have to reduce the isocratic hold. Right,
well,
Z?
that's a very important point that you bring up, and Z brought this up earlier. If you want to develop a robust method, you should always have at least 1 to 2 column volume gradient hold, isocratic gradient hold at the beginning, because if you don't build that into the method to begin with, your hopes of being able to scale that method and transfer that method may be dashed very quickly.
That hold gives it like a fair chance so that all the analytes start at the same point, basically on the head of the column, and then go, because I know the thermal vanquish, I should add that as like, we're blessed at Phenomenex, we're agnostic in terms of instrumentation. We have all the instruments that are out there, pretty much from Thermo to Shimadzu and so on. So we can play with all these instruments, and a lot of the newer softwares like Dr. Phil mentioned, you can actually, for the Vanquish, you could actually type in if you are trying to transfer a method from QC to R&D or so on and so forth. So, and we have equations, I believe, Simon, in the back of our catalog that can help customers do that with, you know, simple math. If they want to do the example that Dr. Phil was mentioning, from going from one dwell volume to another.
Cool, thank you. Okay, back to kind of a troubleshooting question. So I'll throw this your way, Z. Could you give us some possible reasons as to why peak shape on chromatograms would potentially deteriorate quicker than usual?
So peak shape deteriorate. Well, Dr. Phil had hit on that in regards to mobile phase composition failures, whether it's the pH increasing or over time. So there's that. There's also photo sensitive analytes that if you're not using like an amber vial and your main compound starts to degrade and an impurity starts coming up somewhere else, there's also that. But there's not much else that over time, like say for example, you make a run on Friday late afternoon, and then you come in on Monday and try to run it again, you start seeing problems. Those are the two that pretty much stick out. There's also the very rare, but it does happen if you're even in your vial, when the needle makes a puncture, if you have a strong solvent on the inside, the strong solvent starts to evaporate, the analyte will basically get stronger and stronger because it's evaporating. So then you'll start seeing what could be maybe even an overload on your column if you leave it there long enough.
I would just add
the chiller and the auto sampler is your best friend. Like, use it. It's there for a reason.
Yeah.
Yeah, I would just add that, and again, depending, I'm not sure what the context of the question is, but if you're asking over the course of, you're doing the right things, you're making fresh mobile phase periodically, and you're running your method, and then over time you're seeing that the performance of the column is degrading, or that the peak shape is starting to degrade. That's typically because of accumulation of contamination on the column. So again, going back to what Zayshawn mentioned earlier, this is where guard columns can be useful, because it's some, especially if it's an isocratic method, it means that something's accumulating in the column. You probably need to clean the column periodically. So at the end of the sample set, maybe run a high organic and try to flush anything that's strongly retained and not eluting from the column under the isocratic conditions. A guard column helps immensely there because it'll trap that more strongly retained component. Then when you start to see the degradation in the performance, then you just throw the guard column away because it's much less expensive than the analytical column. You just replace the guard. But that's, again, there's no wrong answer. I think that I guess it depends on the context of the question. So I think Zayshawn took one kind of approach as to the way he interpreted it. And so I took another, and I would, and just in general, troubleshooting, if you reach out to our Phenomenex technical support staff, I always like to say that pictures paint 1,000 words. Well, that's not what I said, but somebody said way back in the past, and chromatograms are pictures in a way. So when you start describing problems like I'm having a peak shape issue or peaks are shifting, et cetera, if you can show somebody who's helping you out on a troubleshooting situation the example of what good looks like and the example of what bad is now looking like, that helps to get everybody kind of on an equal communication, and then you can begin diving in a little bit more on troubleshooting. So our technical team is really good support folks out there that can help you with your troubleshooting situations.
So I'll leave this one open to anyone that wants to answer it. Kind of a similar question to, where it's compound specific, but do you guys have any recommendations for analyzing compounds that are highly sensitive to degradation, kind of like vitamins?
Well, I mean, I would just chime in with our Verax vials. We have amber vials that can prevent light from getting into it to degrade it any faster. There's chillers, as Jason had mentioned, to try to prevent anything from getting degraded from from heat. And then I'm trying to think, is there anything else that would help that? Not that I can think of. Anything else, Dr. Phil, Jason?
Well, if you can avoid using pre-slit vial caps, I mean, they're great because they save needles from getting plugged, but they're not so great as in the fact that they're open to the atmosphere from the second, that you put the sample in there. So that's another thing you could do.
Yeah, especially if your diluent is an organic solvent that's a little bit more volatile. But yeah, if you've got compounds that are a little bit more thermally sensitive, then again, to go back to what Jason recommended and Zayshawn seconded is, that auto sampler chiller is your friend. Take advantage of it.
Okay, I'm going to take a step back. I got a question that relates to column lifetime. So, is there a typical, threshold or criteria that you guys have used to kind of measure when you need to replace a column?
I know that some of our parameters, when we look at what constitutes column death, when we're testing columns at their extremes of pH or temperature, I believe we use when efficiency drops to half, so 50% of the original. Obviously, that's not, you don't want to wait that long probably, because it's going to have a dramatic effect on the quality of your separation. I always go back to guidance. I mean, it's really, are you meeting your system suitability requirements? First and foremost, are you getting the resolution, the separation, the peak shape, peak symmetry that you desire? And some of the guidance that I always talk about really relates to using guard columns and when to replace guard columns, but the same would apply to maybe when you replace a column if you're not using a guard column. Pay attention to your system suitability needs. Don't wait until it fails. Replace the guard column, or consider replacing the column well before you fail system suitability, because that creates all sorts of bigger issues. So when you lose 10-20% of your resolution, even though say your requirement is 1.5 and you're starting at 2, so if you lose 10%, you're down to 1.8. It doesn't necessarily mean that you want to replace the column, but you need to be paying attention. And if you're using a guard column and it's doing its job right, you replace the guard column, the performance might come back to very close to what it was originally, because the guard is doing its job and trapping the contaminant that might be affecting that performance. So, and again, the same thing with pressure. Don't wait till the pressure doubles, or until your pump shuts down because you've hit the max value. So kind of pay attention to those chromatographic performance parameters, but also some of the mechanical, like pressure aspects, and that'll give you some guidance as to when you should replace guard columns or even begin to think about replacing a column.
Pressure very rarely, I would say, increases linearly. It's usually an exponential increase. So as somebody that has run more column lifetime studies than I care to even think about for this company, we almost always see that there's an exponential pressure increase. So if you start seeing the pressure go up by 10-15%, don't wait, because as Phil said, it's going to overpressure very, very soon. And his advice about the system suitability, running that system suitability check standard periodically and plotting the changes and understanding how that is going to be it's going to help you replace the problem before it becomes a real problem, and be a good predictor. Because columns can fail because of pressure, they can fail because of broadening, either due to channel formation in the column or plugging up a fritz. A plugged frit doesn't always lead to increased back pressure. It can lead to peak shape issues. And then, there's other things you can do other than, running high organic. Like the idea that running a high organic quote unquote cleanup at the end of a gradient will clean up a column. My experience has been that acetonitrile can be a really crappy solvent for a lot of stuff. And so just running pure acetonitrile at the end of your gradient, I suggest periodically running a mixture of acetonitrile, methanol, IPA, and water, 25% each. That seems to clean up columns a lot better than just acetonitrile alone. So there's another thing that you could use. Internally, we call that the magic wash.
Yeah. Oh, I'd just like to add to that, like when our columns go out brand new, Dr. Phil knows this very well, that when we give our seminars, we tell customers that there's a C of A that comes with every column that we send out, because we test every column. And then it's a good benchmark for you to see what the efficiency was when it left Phenomenex. And then we sell the test mix at Phenomenex too, that you can get from our catalog. And you can run that same test mix at your lab, so you can see where you are with the column once it comes out of the box. And then you just go about 20, as Dr. Phil mentioned, 20 to 30% of its efficiency. If you start seeing that loss, that should be a pretty good guideline to start calling your HPLC rep and try to get a new column.
Yeah, I would just add there that not everybody, and every company and every lab's protocol is a little bit different. Some customers love to run that column test mix and compare with what the vendor has obtained, just to benchmark their result. But more often than not, you're running your system suitability. That's the one that's more meaningful to you for that specific method. And so, as Jason mentioned, it's like plotting it. Don't just run it and, oh, it passed, and then we just keep kind of going. If you start to see those small, and they will be small, differences in terms of efficiency or resolution, pressure is going to be a little bit more noticeable, but, kind of keep track of some of those things so that, and as you develop some history, then you start to get a better idea of maybe how often you should be changing or replacing the column.
It only takes one bad sample to kill a column.
That's true.
Very true. All right, switching to columns themselves, let's focus on selectivity. So I'll ask this because I know you all probably have your own starters for this. It's a good question. What phases or selectivities do you recommend starting with for initial investigations?
Well, I'll start. I would, even before I answer that question completely, I would say, well, what do you know about your compounds? What are some of the structural features? I mean, are they hydrophobic? Are they hydrophilic? Are they basic? Are they acidic? Because that's going to give you some indication as to maybe what pH mobile phase I want to start with. And then what other structural features? If they have phenyl groups, then maybe a phenyl phase is one of the ones I want to screen. Generally, I would, most of us in the reverse phase method development are going to choose our favorite or at least one C18 column. But if there's some of these compounds are more polar, then you might choose a C18 that's got more polar functionality, like a polar C18, for example, or if it's got aromatic groups, phenyl groups, and it's basic or acidic, then something like biphenyl or F5 or phenyl because of the potential for different selectivities and different potential interactions. We have to remember that C18 is, not to denigrate it, but it's a one-trick pony. It's primarily going to separate based on hydrophobic nonpolar interactions. If you rely on a traditional C18 with TMS end capping for polar selectivity, you're relying on residual silanols, which are not controlled as well as the primary bonding the C18 group is. And so that's where polar functionalized phases like polar embedded, polar end capped, or just polar surface C18s, if you still want that C18 selectivity. And then the other structural features like phenyl groups and such to steer you in that direction. But one of the nice things about groups or phases like biphenyl and pentafluorophenol or F5, even phenyl is that they offer multiple potential interactions. So you got pi-pi interaction, you've got hydrophobic interactions still taking place, but you also have some potential for dipole through hydrogen bonding and dipole type interactions. So you got a broader flavor. They're not going to be as retentive on the hydrophobic side as the C18, for example, but so what's your structure? What do you know about your compounds? And then that dictates maybe what pH and mobile phase parameters you might use, and then choose a couple of different phases and screen them. Ideally, that if you have the time and the wherewithal to do that, and you're not asked to complete the method development in 16 hours, then you have a little bit of time to at least try some things.
For myself, it's pretty much exactly as Dr. Phil had mentioned. I mean, we're spoiled at Phenomenex that we have the entire catalog at our disposals. If we need any phases, we just go over to our amazing warehouse and just pick out a column that we need for the application. We also do have column selectors at Phenomenex, so 6 position selectors so that we could put different flavors of our columns on there, and then just basically run the screen. It'll inject the same method, same sample and same method onto each column. So that helps a lot, but being more methodical and understanding your analyte is key to picking the right phase the first or second time at least. And my go-tos are usually are going to be the Kinetics by Phenol, either 2.6 or 5 micron, or our Kinetics Polar or PS. Those are two newer wonderful phases that we offer too.
I'm just going to throw in there, don't forget about Helic. Everybody always forgets about Helic.
Yeah, it's true.
Yeah, for very polar compounds, you know, I mean, a lot of us, you're right, that's kind of taking the approach of reverse phase first and C18 and polar C18s and biphenyl and everything. And then you're like, well, none of that worked, or it maybe it worked, but it's not as good as I'd like. And so, you know, when you screen and you've got 3 or 4 compounds that are eluting near the void on a traditional reverse phase gradient on a C18, that's a surefire indication that they're very polar. And Jason's right, then maybe Helic is the better option to explore, because then the retention time should be much longer for those compounds under Helic conditions.
Cool. Speaking of selectivity and the combination of mobile phase, I think I'll give this one to you, Z. Do you guys have any phases that are high pH stable, either core shell or fully porous?
So we do. We have our fully porous Gemini, Gemini NX, which are pH stable to 12, I believe, right, Jason? And then I commonly use our other phases, which is our core shell Kinetics Evo, which is pH stable from 1 to 12. They're very robust, strong phases. So when you're working with a very basic compound, as Jason had mentioned, when you're trying to find, either you're going to go to the acidic side of the spectrum, or if you can, with this type of a column, go to the far right and go to at least pH 10 or 11, it's nice to have an HPLC column that can actually let you get there, because traditional silica starts to melt around 8. So 8 or 8.5. So these hybrid phases that we offer, the Gemini NX, and the Kinetics Evo, lets you get to those extremes of pH so that your basic compound is happy, and then hopefully retains longer on your run.
Cool. Thank you, Dr. Ansbach. What is the selectivity difference, and I guess the advantages between, you know, a biphenyl or F5 or PFP type phase?
So it's a good question. The main difference is the electron withdrawing groups that are on a fluorinated phase versus just a strictly aromatic phase. When you have a strictly aromatic phase, your charge density on the aromatic ring is going to be higher. Then when you have a fluorinated, those electron withdrawing groups are going to reduce electron density on the aromatic ring. So your main difference is going to be that you're going to get a lot more pi-pi sort of interactions with a non-fluorinated ring, and with the fluorinated ring, you're going to get a lot more polar and hydrogen bonding sort of interactions. They also tend to be a little bit better in shape selectivity. I mean, all phenyl columns add a little bit of benefit in terms of shape selectivity, but the fluorinated columns seem to do just a little bit better than the non-fluorinated columns.
I guess the way that's a good way to explain it. I just add that, just remember that fluorine's the most electronegative element in the periodic table. And so that carbon-fluorine bond on, say, a pentafluorophenyl or any fluorinated phase, you've already got a dipole. So you're going to get a lot of dipole type interaction, and the fluorine atom itself has a lot of lone pair of electrons, so can participate in hydrogen bonding to perhaps a greater degree than you would see with a phenyl type phase.
On that segue, Dr. Phil, thank you for bringing us back to the basics of the periodic table. And everyone on the call, thank you for joining us. To our panelists, thank you for your knowledge and sharing your experience. For everybody that did join or is going to watch this on demand, if you have additional questions, please shoot them across. You can easily get to, our technical team, www.phenomenex.com/chat, or just show up to our homepage and you can find an easy way to hit the chat button, and they'll be there to answer your questions. If we didn't get to your questions on this particular occasion, we'll definitely get back to you. So all the questions that came through, don't worry, we will get to, and be on the lookout for the next set of Inside the Lab. We'll be hitting various application categories and industry, collectives. So one of them being cannabis, and I believe clinical research. We're going to focus one on gas chromatography and continue on from here. So thank you again, everybody. And whether you're staring at me right now or whether you're behind the scenes, in your lab or at home, remember, stay safe, sane, healthy, and keep your curiosity high for chromatography. Okay, thank you.
Bye.
Bye.